Hello. Hi, everyone. Welcome. Good morning, good afternoon, good evening, depending on where you're joining us from. Today's webinar is about Shift Crash. This is the world's first physics AI crash model that we at Luminary have built. We will be going over what went into creating the model, what are some of the use cases, etc. So this is the agenda we have. First, I'll give a brief overview of who we are, who Luminary is, for those of you joining us for the first time. Then I'm joined here by my colleague Ridhiman, who will go over the shift crash model. So he's the one who's created the shift crash model. He'll give you all the nice details about the model. Then we talk about some of the use cases, which is a hot question we get asked a lot, like we have a fast running model, so what? And finally, we'll have around 10 to 15 minutes for Q&A. Some housekeeping stuff before we get started. There is a Q&A button at the bottom bar on Zoom. You can use that to post your questions, and we'll try to get to as many questions as we can today. And on the same button, on the same bar, there's also the resources button that you can use to download any of the data sheets or go to the blog where we go into a lot more technical details, or you can go to our website where you can try Shift Crash for yourself in real time. With that, I'll start with a brief intro. I'm Dheeraj Vemula. I'm a technical marketing engineer at Luminary. I've been in the simulation space for about 9, 10 years now. Been in different functions, spent some time in the automotive industry, then did a lot of digital twin stuff, but my expertise is simulation, reduced R modeling, optimization, physics AI. Over to you, Ridhiman.
Hi everyone, I am Ridman. I'm a forward deployed engineer at Luminary working specifically on simulation and physics AI. I recently graduated from Penn State with a PhD in mechanical engineering and computational science, and most of my work was in developing uh, graph neural network models, neural operator models for multiphysics simulations. So, this kind of work it was was a strong step in the right direction for me for my research interest for my work as well. So, yeah, I'm glad to meet you guys and excited to talk about the work that we have done.
All right. Thanks, Ridhiman. Um, so a little bit about Luminary, who we are. For those of you who haven't heard of us before, Luminary is a physics AI company. So what we do is provide this platform where you can build physics AI models end to end. What does end to end mean? Starting from the data, not just simulation data from our own solvers. We have a GPU accelerated CFD solver, which is the fastest in the world, but you can also bring in data from our any other solvers or any open source platforms. As Rhythman will show you later today, how you can incorporate data from external sources. So we start with the data, we ingest all the data, we have the platform help you prepare the data for physics AI, then build the model, train the model, training, validation, all the functions that go into that, and then finally deployment. So we have this end-to-end pipeline on the platform where you can build physics AI models from simulations at scale. We also have these platform layers and model lifecycle layers that help our platform be extensible so you can connect to your existing workflows. You don't have to, we don't want you to reinvent your existing workflows. We want to integrate into those. So for that purpose, we have an API, SDK API. We have an MCP server. If it's a more agent-driven platform, we have an AI assistant on the platform. It's quite helpful to do everything through chat. We also, and on the back end, have this model lifecycle system where people are not just doing the physics AI models as one-off, right? They're putting these in productions, doing multiple models. So we have this model lifecycle that supports a many number of models that you built, version controlling, audit trail, and governance. So a complete platform that takes physics AI into production, not just one off a bunch of different scripts that tied together, but something that's production grade and ready for your enterprise. With that, I hope you have a good picture of who Luminary is. And now I'll hand it over to Riddiman to talk about Shift Crash.
Thank you so much, Dheeraj. All right. So let's dive right into it. We're going to talk about what went into developing this model, what went into developing the data set, and what you would expect to see out of a model like this, the use cases, and so on and so forth. Um, all right, so let's get started. So one of the sticking points why we decided to pick up this problem is that crash simulations are expensive across the board, right? Whether you're doing simulations for full vehicles or if you're doing tests, it's a lot of time, it's a lot of compute, it's a lot of money. Um, uh, a single full vehicle crash simulation can take anywhere from around 10 to 12 hours on an HPC cluster. And it's not always just about the runtime itself, right? It's about, a designer or an engineer submitting a job and the job stays in queue for a few days. So by the time you actually get to those results, it might take you 3, 4 days or maybe even a week, right? So speed is of the essence when you are designing a new vehicle for a new vehicle program, for example, and you want feedback for your what if scenarios. What if I make an adjustment here? What if I change the shape of the rails? And if you have to wait a week or even a few days for that feedback, um, you're losing a lot of time as well as engineer hours. Um, this also ties into the fact that once you have made certain changes to your design, you have these design decisions locked in because of the amount of time and expense it takes to compute these. So you have a lot of constraints in your design space. You have less freedom, and finally, when we talk about physics AI at large, we see a lot of applications in external CFD in smoother distributions. Crash is something that is less seen in the literature because of its highly nonlinear and highly localized behavior. And so we wanted to tackle this problem from a nonlinear FEA perspective as well. So what we have contributed to this body of work is twofold. First, we have provided the largest available crash data set out there. So we have around 5,000 simulations of parameterized geometries, the base model of which is the 2010 Toyota Yaris. Um, and we are looking only at a full frontal crash at 56 kilometers per hour or 30 miles per hour, which is the NHTSA NCAP standardized full frontal crash test format. The model predictions are workflow ready, and what I mean by that is that the model predictions are accurate enough to treat it as you would treat a simulation output. So if you want to do downstream calculations on top of the model predictions, if you want to do your QOIs and other analysis, you are set for that. And finally, we are using the Toyota Yaris geometry, which is one of the most validated and extensively studied geometries out there. So it gives us a lot of confidence, and we are coming from a position of strength in terms of both the data set and the model. So in a physics AI workflow, you would probably be looking at a workflow like this. You will have a base geometry, which in our case is the Toyota Yaris. You would create a parameterized design space out of it by changing, say, some material parameters or some design parameters. And once you click on the inference button for the model, you would ideally expect a full field transient behavior of the car to see how it deforms. You would also see the von Mises stresses to see how the loads are being transferred over the entire body of the car. And finally, you would want to analyze and generate your own quantities of interest or QOIs. We have looked at firewall intrusion, acceleration, delta V in our case, but you can use your own quantities of interest as you would like. So the way we look at physics AI is, it's not to replace simulations, but to augment your simulation workflows. So physics AI gives us the opportunity to explore thousands and thousands of designs, thousands and thousands of what if scenarios, and you would be able to down select. You would be able to rank and filter by your quantities of interest. And once you have a good candidate pool, you now submit your full high fidelity simulations to validate your physics AI predictions. So what this is basically doing is de-risking your actual simulation runs, giving you more bang for money for your compute and for your time. So in terms of let's talk about the geometry parameterization in this case. So we're looking at 4 geometric parameters and 2 thickness and material parameters. The reason for doing this is we want to show that our model, responds to changes in materials, changes in thickness, in sheet metal thickness, but also it generalizes to different kinds of changes in the geometry itself. So for geometry, we are looking at changing the front crush zone, which absorbs the most amount of energy in a frontal crash, the cabin length, which directly affects the passenger survival, the roof height, which changes how the loads are being transferred onto the passenger cage, as well as the car width, which changes the center of mass. For thickness, we are changing the thickness of the front rail, which is the most energy absorbing part of the front area of the car during a frontal crash. As well as the material of the front rails, we're going all the way from mild steel to dual phase 600. The design variables are uniformly distributed across the entirety of the data set. And this is a sanity check for everyone, right? We don't want the design variables to be stuck in a certain corner of the sampling space. We want the variables to be uniformly distributed so that the model learns uniformly and there is no bias involved. The Pearson correlation also shows that changing one variable does not change the other ones, so they are actually independent of one another. The end-to-end workflow for training is something that that's pretty standard. So we have 6 design variables, and we have generated about 5,000 variants from that. All simulations are run using open radios, while the parameterizations were done in ANSA. The simulation time is about 120 milliseconds, which gives us 13 frames at 10 milliseconds each. As discussed earlier, we're looking at the 56 kilometers per hour for a full frontal crash. So once we clean our data set, the outputs are the deformed positions of the car over time, as well as the von Mises stresses. The model is trained using our own version of Geotron Solver. It's pretty lightweight. It fits on one H100. It even fits on one NVIDIA T4. The model is trained using 1,000 cases, not the entire 5,000 cases of our dataset, but the 1,000 cases which are also selected uniformly from the dataset. And this is trained using DDP across a multi-GPU, across 8 GPUs here over 72 hours. During inference is pretty cheap as well. For on an NVIDIA T4, it takes about 50 seconds for the entire temporal output of the model. We are predicting deformation and von Mises stresses, and quantities of interest like firewall intrusion, deceleration, delta V. These are all calculated from the model predictions themselves. All right, enough about the setup. Let's now dive into the exciting part, which is the results. So here's a case that the model has not seen at all before. On the left, you can see the ground truth simulation output from open radios, and on the right is the model predictions. You can see that they're almost virtually indistinguishable. And it's not just the outer shell of the car that's deforming, but if you look at the front window, which is getting a little pushed forward, and there's a seat behind, which is also lurching forward. So this is not just the outer shell, but it's the entire car system which is going through deformation and like temporal changes, right? And this is exactly what we want to see, right? How the components inside the car is moving around, how the engine is moving around, how the so if there is any intrusion, it should also happen inside the car as well. And not just deformations, but we're also predicting the von Mises stress here, where you can see how the loads are being transferred onto the top of the passenger cage. On the right side, we have the error plots. Since most of the behavior is happening in front of the car, we also expect our errors to be, accumulated in the front of the car. Um, the good thing here is that our errors are about 10 to 20 millimeters even in the front, which is quite comparable to our element size of the model, which is about 12 to 16 millimeters. So the model predictions are trustworthy enough. I mentioned the model's behavior being trustworthy, and what I mean by that is that we have insights into why the model is learning the things that it is learning. So just to give a brief overview, the model learns to accumulate to assign slices or point clouds to different regions of a geometry depending on its behavior. So in a frontal crash, we would expect most of the car to not be deformed, right? The back of the car should not be deformed, and this gets one big orange slice. However, most of the behavior is happening in the front, and there are different modes of crashes, different modes of failure, and the model is learning that by assigning these individual color blobs to different regions of the front of the car. And it's not just the frontal bumper, but also, as you can see on the underside of the car, it's different components inside the car that's getting these specialized treatment. And that is how the model is learning the different crash responses without any sort of manual tagging from our side at the component level. The model is learning all of this all by its own, and this allows us to trust the model's prediction as something beyond just a random guess. So now that we have seen the full field behavior, let's talk about the quantities of interest which are calculated directly from the model predictions. So here we are looking at the peak deceleration across three different cases. So the first case is an all main geometry case. So, short front rails, thin rails, low yield strength material. You would definitely expect a more severe crash to happen in this case, and that's also shown in the model, shown in the graph here. You have the lowest peak acceleration or the highest peak deceleration, which is a proxy for in your crash severity, and it's also a proxy for head injury criteria. You can see that the peak deceleration calculated from the model is almost a direct overlap of the ones that's calculated from the simulation data. And across all test cases, we capture it within 3% of simulation data. So we are we feel pretty good about the model's overall predicting capability. You can see that for the other two cases as well, which is a mid-range case and a mixed case, the prediction data is almost on top of the simulation data. Um, Next up is firewall intrusion. Firewall intrusion, of course, it determines the driver's survival when he's sitting in the driver's cage. When during a crash event, the engine is going to move in and it's going to intrude through the firewall, and we need to understand how much this intrusion is. For our all main case, actually for all of our cases, you can see that the trend is being captured by the model really, really well. The simulation output is almost completely superimposed by the physics AI output. And finally, we have delta V. So since crash is a rebound event, when the car is rebounding from the wall, if it has a higher velocity, it means that it has undergone a more severe crash, right? So once again, in the first case, you would expect a higher delta V to account for the severity of crash. You can see that's the case here, and also the model captures the trends across all three cases really well. Throughout our test case, it calculates delta V within 2% errors for all test cases. And we always get asked this question, how much data is enough data? This really depends on your application, right? If you want a really, really accurate model, then you probably want to feed more data to the model. But if you want directional accuracy, you can get away with a lot lesser than that, right? And we did this study. We found that to get to a sub-element level accuracy, which is around our element sizes are 12 to 16 millimeters here for a coarse mesh. But to get to a sub-element level accuracy, you need around 300 cases. Um, so you can start to see that the curve starts to flatline a little bit. And once again, I want to reiterate that we trained the model on 1,000 cases, not even the full 5,000. So the more data you push into the model, the more accurate it's going to be. So throughout this entire exercise, we have shown that we are able to ingest, we are able to plug into your workflow pretty seamlessly. If you have LS-DYNA data, if you have radios data, or meshes from ANSA, we're able to make use of that right out of the bat. We have connectors developed. We're able to ingest that data, train our models on top of it, and there's a lot of scope for improvement of these models as well, right? We want to add dummies into the model to understand head injury criteria, to understand seatbelt modeling, to do airbags modeling, and all of those kind of things. We are able to deploy anywhere, as Dheeraj has previously mentioned. We are able to deploy on the cloud, on your private cloud, on-prem, anywhere that you would want to have this capability on, and your data does not need to leave your system ever. And finally, we see this as a very promising direction for transfer learning as well. So imagine you already have a trained model for a particular vehicle program. You want to use that knowledge to transfer to another vehicle program, and you need to generate only a tiny amount of data for your new vehicle, and you can retrain the model to fine tune it onto your new vehicle. Yeah, that's what we had in terms of the model and the data set. Over to you, Ziraj.
Thanks, Ridhima. Hopefully you got a good idea about what went into building Shift Crash, the first physics AI model for crash simulation, full vehicle crash simulation. Now I want to go into some of the use cases. What I mean by use cases. We often get this question whenever we talk about physics AI with our customers is like, yes, I have a fast running model, but now what? How can I use that? What does it actually unlock for me? So in order to understand that, let's look at some of the challenges, specifically in the automotive industry, that we see today, that we hear from our customers. One is complexity, right? Now, SDV, software-defined vehicles, are becoming increasingly a popular trend. So machines are becoming complex and are being developed at a pace that softwares are usually developed, which is different, very different, and a step change for the automotive industry. This doesn't only mean that your development has accelerated super fast. It also means that there are a lot of different connected systems that need to work well with each other. So the complexity of these multi-physics, multi-domain systems means a lot more validation, and safety has been the biggest bottleneck in validation, because it's the most important thing to get an automotive mobile certified for the road, but then it's also the most time-consuming step that occurs much later in your design cycle. It might push something like start of production, some of the metrics that matter for you when you're trying to introduce a new vehicle into the market. And finally, not having an early understanding of your full system means that there is a large risk in rework much later in the program. If you have to make even a small change before you go into production, that means you need to retool your production plan, you need to do configuration changes, and you have to push out your start of production or time to market. So these are some of the challenges we hear from our customers when they are trying to think of how can I address these challenges? How can we solve this with physics AI? So what we want to show is three different use cases that are built based on just one shift crash model, but touch different areas of your product development lifecycle. The first one is accelerated crashworthiness through AI model-driven optimization. So as Rhythman talked already, the Crash is a very complex simulation with a lot of design variables, a lot of requirements that are important when you're looking at a crash simulation. And creating an optimal design, it's not a humanly possible task. It needs to be an automated loop. It needs to be a rapid and a wide exploratory journey. And it's not a one and done either, right? Because we see optimization being done at different stages of the vehicle program as the requirements change, your adjacent systems change, your package requirements change, your design requirements change. And often the objectives you're trying to optimize for are conflicting with each other, right? Like you have, for example, weight and safety are often these conflicting trade-offs. If you increase weight, you will you're trying to minimize weight, but then if you do that, you're trying to increase the risk of safety. So uh, so evaluating all of these design combinations for this complex optimization can be hard and even if you're able to do it in an automated fashion, can take a lot of time if you're doing a full fidelity simulation. That's why physics AI has an advantage. You can rapidly explore thousands of designs within an instant using physics AI. So I will now switch to a demo to show our optimization dashboard. While I do that, I want to also say this about optimization. Uh, as I mentioned earlier, uh, this is not something you need to incorporate into your workflow. You can, this is not meant to reinvent your workflow, but you can build your own, build the optimization into your workflows with through the API SDKs. You can build into the workflows. Hold on a second. I'm having a bit of an IT issue. Let me share a minute. Yeah. Okay. So here's an example of how optimization might look like, right? And like I said, this doesn't have to be your solution, but you can integrate, let's say you're using your own optimizer like an Esteco tool or an OptiSlang. You can easily integrate the physics AI model into your optimization tool. But just to demonstrate the idea, let's say you're trying to optimize for both weight and safety. You're trying to do a trade-off study. You can run a multi-objective optimization using an algorithm like NSGA, a genetic algorithm, evaluate thousands of designs really fastly, and not just I get one optimal design, but have a Pareto friend that you can choose from. Like it gives information about like how your key metrics are and what your design looks like, right? And you might just as well do different types of optimization. Maybe you're not doing the multi-objective study, maybe you're just trying to minimize weight early in the program. So you can do that too. So the idea is you can do multiple optimizations through the model just once. Once you have the model ready, you can do multiple optimizations as many number of times as you want. So that's the value in optimization. If you're doing one-off optimizations, it might be easier just to do the full fidelity simulation. But assuming you are going to do this as your program requirements change, as your design changes, the reusability of the physics AI model is really strong. Um, Let me switch back to the slides. Sorry, I'm having an issue with Zoom today, but you should be able to. Okay. Okay. The next use case is a physics informed design studio. And this goes into this idea of left shifting your design freeze, right? One of the common challenges we hear from our customers is that there is a big disconnect between designers and analysts. They don't speak the same language, they operate at different speeds, which means like they're in different silos, unable to understand each other's intentions and each other's requirements. So, what traditionally happens is a designer comes up with a bunch of designs, then they throw it over the fence to your analyst, then they analyze the designs, they find out which ones meet their requirements, and then they go back to the designer. There's a whole manual iterative process which can take weeks if not months. But what Physics AI Informed Studio enables is that having that physics feedback right in your design studio environment. You don't need to go to the analyst when you make small design changes. You can evaluate the performance of your design right in your design studio. And maybe you come up with a smaller set of finalized designs that are more performant, that are more closer to your design requirements, and move them to the analyst so that they can analyze the final set of designs and come to the optimal design. So this not only is more collaborative, it also means less rework, less time to come to the final optimal design that both the designer and analyst can agree on. Now I want to show a quick demo of how this looks like. Just a minute. Okay, so we are in the physics-informed design studio. Again, this is our environment, but you don't have to do your design in our environment. This can just as easily be in an environment that you're used to designing, for example, like Blender. So you're a designer, you're trying to change the design, uh, make some tweaks to the design, adjust the parameters, and you wanna, at this point, normally what you would do is pass on the design back to the analyst to understand how the design changes your crash performance. Instead, in a physics-informed design studio where the physics AI model runs in the background on the new design that you've created, tells you instantly like what the impact of that design is. You're a designer, you don't care about the stress field, but you want to know whether it's within the spec of your performance requirements or not. So it gives you a breakdown of where it's not meeting the requirements, and you can quickly change or maybe adjust some of the parameters. You know, there is a material selection available, so you can adjust those parameters and see how that impacts the design. So this enables this fast physics feedback that can help you come up with better designs easily, and not just as a designer in your day to day, but this also improves collaboration because a designer and an analyst can get into one room immediately. Do a design validation study. They can quickly change the designs and understand what the impact is, and come to a quick design as opposed to waiting for a full fidelity simulation that takes weeks to run. So that's the design studio. Are you seeing the presentation now? And then the next use case is multiphysics systems for battery thermal runaway. So, so there is this increasingly complex vehicle architectures where different systems are connected together, right? And one of the things we've looked at is how does crash impact thermal safety? Battery runaway is a big safety concept for EVs, where any cell intrusion can lead to potential thermal runaway, which can be catastrophic. Uh, and this again, like the designer analyst problem, has been looked at in a siloed, separate way. So a battery analyst would look at the thermal runaway, a crash analyst would look at crash. They're in their own siloed development, but they're not talking to each other. It's the systems are not connected to each other, whereas in real life they are one single system with connectedness throughout. But the challenge or the problem with looking at these siloed systems is that you end up over designing your car, making it heavier, less range, less performance. But with physics AI, now you can move to a coupled crash thermal runaway where a crash system is the crash system's outputs are connected to your thermal runaway simulation. And for now, we will show a one-way coupling, but you can do a two-way coupling too on this. What that help enables is that it's gonna reduce your thermal runaway risk because there is the transient aspect of the crash simulation. You have the time component now available to you as opposed to just saying this much of intrusion is bad. So what that means is you can plan for your fire suppression strategies given the time to thermal runaway risk. You can identify critical intrusion depths, etc. And what it unlocks for a vehicle program is an optimized design that is safer and lighter. Now let me jump to the crash thermal runaway demo. Uh, Share. So this so this uh, demo again, it's using an open source Python library for demonstrating the thermal runaway. PyBAM is a popular library that models cell chemistry and everything. So the the crash results, we are using the peak firewall intrusion as a proxy for the thermal runaway simulation. In real world, you can get into the cell intrusion level also from the crash simulation. You can look at side impact. That tells you that's one of the most critical types of abuse scenarios for thermal runaway for an EV. So there are different things you can look at, but as a proxy to demonstrate the idea, we are showing you here the peak firewall intrusion as a proxy, and the value for the peak firewall intrusion is pulled from the Design Studio app. You then run the simulation, and then this is a fast, lightweight model, so it runs immediately and tells you the risk of thermal runaway. You can check different intrusion values. You can run, let's say, a lower firewall intrusion, and see that reflects or that results in a stable cell. So you can do more connected multi-physics systems level outlook using a physics AI model. Absent of a physics AI model, you'd have to, every time a design changes, you have to go back to a mesh, you have to go back to solving it and waiting, whereas the simulations, as you can see, are at different scales, different speeds, etc. So, so that's the final use case. I wanted to show some of the future work we are focusing on for Shift Crash. I'll maybe let Ridhiman talk about this. Let me.
Yep. Thank you, David. Um, yeah, I think first of all, thank you for the demos. I think that paints a really nice picture of how this can be, utilized in different kinds of workflows. And we want to support more. We want to push the boundaries. We want to keep pushing on boundaries with our crash work. And one of the things that we are really interested to bring into our portfolio of predictions is effective plastic strain. Um, so we have heard that whenever crash engineers are looking at crash models, they are interested to learn where a material fails, where a material yields, and so plastic strain seems to be quite important to understand material failure inside the model. So So that's one thing that we are actively working on right now. We are also introducing principal stress components, so that gives not just the one Mrs. Stress, but all of the entire stress matrix to the hands of the principal design engineer to make more informed decisions on the structural loads on the car and basing design decisions on top of that. And finally, in terms of material failure as well, we also want to include probabilities for element deletions. So those of you who are savvy with crash simulations, you would know that when you're running a crash simulation, there are certain elements that get deleted from the simulation when they fail a certain criteria, like a cost criteria or a JC criteria, and we want to also provide the simulation engineer with the idea of what nodes are getting deleted and where they're getting deleted, which probably would mean that there is a negative volume there during the simulation, or maybe there's artificial energy injection there during the simulation. So, yeah, those are the kind of things that we want to add in the near term to our crash model, with a bunch of future work that we are also thinking of, for example, spot wheel failures and all those kind of things. So yeah, we are excited about what we can bring down the line. Uh, so in summary, I think what we were able to show that crashworthiness is a difficult problem, but physics AI is ready for it. We have our models to show that. We are able to show that at a production level, not just not just in a one-off scale. We are able to get sub-element accuracy with relatively little data, and of course, the accuracy that you would need depends on your use case, and the data should scale according to that. Field predictions are accurate enough to use for downstream calculations. You would treat them just as you would treat your simulation data. So once again, you don't need to change your workflows at all. Um, and yeah, we are looking at faster design decisions based on your what if scenarios. We are talking about introducing more collaboration between teams that maybe did not have as linked of collaborations before. And we want to left shift the entire design decisions to account for more collaborative design development. And maybe we want to see more beautiful designs. We want to see more collaboration, more understanding about the entire field, and that helps us grow, helps all of us grow. So over to you. Yes.
All right. So as I mentioned earlier, we have all the resources available for you. You can download the Crash data set. You have access to the demo that where you can try Crash for yourself. You can contact either of us if you have more questions. We'll be always happy to answer your questions. And we are also hiring. We are actively hiring for a number of different roles. Do check out our careers page if you're interested in. With that, I thank everyone for joining, and now we'll take any questions you might have. Let's see. Okay. I think the first question is, how can someone use this model? Is this a hosted model that someone can access with an API call? I think they're asking specifically about the crash model. Maybe, Ridhman, do you want to take that?
Yeah. So right now, what we are offering is, the model weights are available open source, but to actually run this model, you would need to be a part of our platform and call this through our SDK API. We have inference. You can either run this model in our app on the website, or you can also run this through our SDK, which is a Python scripted environment. So yeah, once you're on our app, you would get an API key, and you would be able to run our model there. If you do want to try out the demo, to see how this model behaves, you can always go on our web app and see how this actually works underneath.
Yeah, so that's specific to the crash model, but let's say you created your own version of the crash model or any other physics AI model on the platform, like Pridhiman already mentioned. So it's there are different flavors of deployment. So you can deploy it on our cloud infrastructure, or we also offer a virtual private cloud, so on-prem, air-gapped environment, etc. So depending on where you want to deploy, all the possible combinations are available. The next question is how would these models perform for composite structures? What changes?
Yeah, I think I can take that question. Alejandro, thank you for the question. So what would change for a composite structure model would be the parameterization itself, right? So you would want to provide information about what kind of composite structures, like are you looking at different material properties for different areas of the design. You would probably want to feed the model that information, retrain maybe a part of the model to fine tune it onto your composite structure model, and then yeah. So in terms of the architecture, not much. In terms of your parameterization, that's the only thing that you need to feed to the model.
I think the next question maybe is also kind
Yeah.
of related, but different domains. So the next question is like, what's the major challenges between training a crash model versus CFD? Um, I'll let that I'll let you answer that.
Yes. Kiran, thank you for the question. Um, I think you've hit the nail on the head here. The reason why you see physics AI being more popular in the CFD field is because CFD fields are smoother, the gradients are easier to work with. In Crash, as you have seen, it's not the case, right? It's a very localized behavior. Um, and we had to do a lot of sort of internal testing and studies to see how to capture this localized behavior. That includes upweighting certain regions, upweighting certain losses, and a lot of engineering work to change the existing the open source geotranssolver version into our very own flavor. So a lot of engineering goes there to sort of make the model understand localized behavior and mesh independence. So I think the fact that crash is such a localized problem makes it really really hard. But that's also the challenge that we took up, and we succeeded with that one.
I think the next question is also kind of you kind of answered that. Like the question is about model is trained on GeoTranssolver. It's a paper published by NVIDIA. How is this different from that paper?
Yeah. Jeeves, I'm taking that question. First of all, thank you for the question again. To add on to what I answered for Iren's question, the reason it is different is multifold, right? So in order to make the existing geotranssolver model work for Crash, we had to do a lot of internal improvements. We're talking about upweighting certain regions of the mesh. We're talking about loss engineering. We're talking about changing the way we are doing the temporal rollouts as well. So all of these had to be very carefully engineered to meet the specific requirements of Crash. So we end up with an architecture which is quite different from the open source geotranssolver version.
You can take the next question too.
Awesome. So Murali's question is, how many models would be required to capture the trend for one segment of the vehicle? Um, uh,
Maybe it's
I, I'm assuming, Murali, you mentioned that like you wanted to know how many data points it would take, like how many different parameterizations, or are you talking about how many different physics AI models?
I think maybe Murali's question is about like one segment is one type maybe
One
sedan.
vehicle archetype.
Yeah, I
Yeah.
think so.
So right now, what we are developing is focused on vehicle archetypes, right? So we have one model that is working on a compact sedan like that. The idea here is that when you're say moving to a different vehicle archetype like a like an SUV or a coupe or a hatchback, you do not need to throw away all of the learnings that you have had when you're training this sedan model. You should be able to take this model, you generate a very tiny amount of data. We're talking about a few hundreds, not in the thousands, even a few hundreds. Um, and then tune your model, the sedan model that you have, for your new vehicle program. So once you have a good trained model for a particular vehicle program, the reusability factor comes into play, and your vehicle programs get faster and faster and faster.
The next question is
Yeah.
also maybe for you.
So um, uh, Srinivasan's question is for the crash model. How many models for train were trained for the demo case, and how were the predictions validated? Uh, Great question, Srinivasan. Thanks for the question. So for the model that we have shown, we trained it using 1,000 cases from our 5,000 case data set. The predictions were validated using about another 500 cases. And we compared the model's performance with the simulation outputs that we already had, right? And we validated the model's predictions, not just using the fulfilled predictions, but also from the quantities of interest that we had. So we showed you that, for different quantities of interest, we have about 2% or 3% error for all of them. So they are well within, within tolerance.
I can take a stab at the next question, and then
Mhm.
we can you can add your
Yep.
points, Ridhman. Um, so the question is about like if every major design iteration still requires a fish explicit FE simulation for validation and data set enrichment. Where is the actual reduction in CAE effort and computational cost? That's actually a very good question. And I mean, it's I think for physics AI always has been the most commonly asked question is what's the ROI of the initial cost that I spend a lot on creating a simulation? Sorry, creating a physics AI model. So the ROI would be in the reusability of the model. So as you've seen here, like the physics AI model once created can be used for different use cases, like in a design studio, an optimization environment, or maybe a multi-physics system. So there's that component of reusability uh, once you have the model well validated. And then there is also what Riddiman talked about, the idea of transfer learning, right? Maybe the initial model does take a large number of simulations, but once you have that, now fine-tuning the model will take a lot less amount of data. And without having that, again, every time you're fine-tuning, you don't have to incur the heavy cost. So that's where the advantage is. Like if you're upfront, you know that you're going to just use this the one time. I think it doesn't make sense. There is no real value. Only when you see a wide application for the model is when we see most of our customers having some value. If you want to add anything to that, Rhythm.
Yeah, I think especially in the design phase, when you're coming up with your newer and newer designs, you want to have sort of a report or an information about uh, what models, what designs work, what designs don't work, and you're sending that out to the downstream production teams, and the production teams. Uh, Probably want a conservative design that fits their requirements, and the design team wants to work wants to give them a conservative design that works with their requirements, so that there is no rework loop, or very little rework loop between the creative phase and the production phase, right? So what we are trying to provide here is a more collaborative environment between the two. So even though it requires a few CAE runs or a few simulation runs every new vehicle program, the number of CAE runs actually reduces when you have a trained model. So maybe when you're in your second vehicle program, it reduces by 50%. On your third vehicle program, it reduces by another 50 or 75%. So you when you go from one vehicle program to the next, maybe you need 200 simulations. To the next one, maybe you need 50 simulations, and that's how you see the compounding go on.
And also, it's not, I mean, depending on the accuracy, it's not necessary that you always
Yeah,
8,000 simulations,
exactly.
right?
Yeah.
I think the next question is more for you. How does the model handle localized features?
Yep. Alejandro, thank you for the follow-up question. Yes. So the model the model's performance is actually uniform across these contact features, and we have monitored the contacts really closely. There are as you know, that there are hundreds of contacts in these highly in these high fidelity meshes. So the error is actually uniform because the model sees these contacts and the differences in their behavior across the entire data set. The model has more challenges anticipating areas where there is translation and rotation, so specifically the wheels. You would be probably seeing a little more error blow up in those regions, but they are not as important as the contact regions themselves in terms of a crash simulation. So actually, in these contact regions, the errors are quite uniform across the board, and they're quite low across the board as well. So
I think we have time for one question. Maybe the last question is, I mean, I think there are two questions actually. Hyperparameters and data set size.
yeah. All right. Yeah. Yes. Prasad, thank you for the questions. Yeah, I'll take a quick stab at both of them. So as far as the hyperparameters are concerned, I'm not probably going to disclose the actual values, but what I can tell you is that we used Bayesian optimization to figure out the best hyperparameters for the model, and for that we did ablation studies, and the basically state of the art for model training before we kick off large amounts of runs. So if you have a certain amount of data, probably your hyperparameters are going to look different, but the workflow would remain the same. You would take a little bit of the data, you would tune your hyperparameters on that, and then kick off large runs, so we are not burning compute or we're not burning resources. So yes, they are optimized for this particular application. The tool takes care of it automatically. The training it's built into the training pipeline, and if for your data set, once again, the hyperparameters are not going to look the same, but they will be optimized for your case. Secondly, along with the data set of 5,000 samples, are there any scenarios to understand and learn about the physics rather than so that the model is good for? That's a solid question, and that's part of our roadmap as well with Shift Crash. So for this particular case, we wanted to take the NHTSA frontal crash scenario, right? But we are augmenting our data set as we speak with pole crashes, with side impact crashes. That should give the model an even broader sense of different kinds of crash scenarios. Maybe 40% overlap is one of them. So we are looking at creating a much larger data set with all of these crash scenarios involved, and we are hopeful that the model is going to generalize well to different kinds of physics scenarios.
Okay, I think that's the last question.